Okay, in this video we're going to be looking at some ways of solving exponential equations when we are given a value for our dependent variable and we want to solve for our independent variable. And then we're also going to be looking at some related topics called half-life and doubling time. So let's take a look at example number one. Example number one says a 200 microgram sample of carbon-14 decays according to this formula, where T is in thousands of years. And the first thing it says is sketch a graph of the function. Okay, so I've got this function here that's given to me. I know my initial value is 200, and I know that it's decaying. And I know it's decaying because my factor here is less than 1. So I'm going to start at some value of 200. And it's going to be decaying, so exponential decay. My graph is going to look something like that. And let me go ahead and label my independent and dependent axes. So my independent axis, that's going to be in time t, and t is in thousands of years. So let me label that here. Thousands of years. And my dependent variable, let's see, is q, and q is in micrograms. Okay, so there's a sketch of my graph. Now it says estimate when there will be 25 micrograms of carbon-14 left. Well, right when I start at time t equals 0, I've got 200 micrograms, and since my amount of carbon-14 is decaying, at some point there's less and less carbon-14 available. At some point it's going to decay down to where there's only 25 micrograms left. So what I would like to know is, what is this value here for t that corresponds to when the number of micrograms reaches 25? Well, I can find this value by using my graphing calculator and entering into y1. Put this right here. I enter into y1 my function here, 200 times 0.886 to the power of x. X is the variable that the calculator uses. And then I'm going to enter into y2 just this constant value of 25. And now, when I graph both of these on this same set of axes in my graphing calculator, I get a graph that looks something like this. Here's my function, my exponential function, and here is a straight line that represents basically y equals 25. And I want to know what is the value of t, my independent variable, at this intersection point. Well, I've got a function on my graphing calculator. It's right above the calc button. And if I hit that, I say second calc. It's right above the trace button. I say second trace, and the fifth one down says intersect, and that helps me to find this intersection point. I just enter in these two values, select these two curves, these two functions, and it tells me what the intersection point here is. In fact, what it tells me is when q, that's my dependent variable, when q equals 25 micrograms, my value of t, that's my dependent variable, is equal to 17.18. And now remember, this is in thousands of years. So this is 17.18 thousand years. Or I could say t equals 17,180 years. So that's how long it takes for 200 micrograms of carbon-14 to decay down to 25 micrograms. Now, let's talk about half-life. Half-life is the amount of time it takes for a quantity to decay to 1/2 of its original value. So, example number 2 says, what is the half-life of carbon-14? In other words, how long does it take for an amount of carbon-14 to decay to half of its original amount? And there's a hint there. It says, hint, what if you started with 200 micrograms of carbon-14? In other words, what if we had this exact same graph? We've got our 200 microgram sample of carbon-14. It decays looking like this. And we already figured out that it takes approximately 17 2.18 thousand years, for that 200 microgram sample to decay down to 25 micrograms. This question is saying, how long is it going to take this 200 microgram sample to decay to half of that value? Half of that value is going to be 100 micrograms. So basically we want to do the same thing that we just did, except we don't want to know how long it takes to decay to 25 micrograms. We want to know how long does it take to decay to 100 micrograms. Well, I'm going to do the same thing that I just did. That is, I'm going to enter into my graphing calculator y1 equals, same equation I had before, 200 times 0.886 to the power of x. For y2, I'm going to enter in 100, and it's going to give me these two graphs here, my curve and this straight line for y equals 100. And again, I use my intersect function on my calculator, and I find that when q equals 100 micrograms, t equals 5.73 thousand years, or 5,730 years. So 5.73 thousand years is this point right here, and that is the half-life of carbon-14. Now you notice there's also another question there that says, what if, it says, what would the half-life be if you started with a different quantity of carbon-14? In other words, there was this little hint here that says, you know, what if you start with 200 micrograms of carbon-14? This question says, well, what if you started with a different amount of carbon-14? What would the half-life be then? And I'm going to leave that for you to think about. We'll talk about that a little bit more in class tomorrow. Doubling time is the amount of time it takes for a given quantity to double in value. So you can see doubling time is kind of like the opposite of half-life. For doubling time, however, you have to have a quantity whose value is not decreasing. You have to have a quantity whose value is increasing. In other words, it's experiencing exponential growth instead of exponential decay. So we have one of those in example number 3. It says Jack planted a mysterious bean plant just outside his kitchen window. It was 2.56 centimeters above the ground when he planted it at 8 a.m. on day 0. And here is Jack's recording of the height of his plant each day at 8 a.m. after day 0 when he first planted the plant. So part A says, write an exponential equation to model the height of the plant as a function of time. Okay, so I know how to do that. I can enter these values into list 1 and list 2 in my calculator. I enter my independent variable into list 1. I enter my dependent variable into list 2. And my calculator, I'm going to use my exponential regression function, and my calculator will tell me that h as a function of t is going to be equal to 2.56 times 2.5 to the power of t. All right, so now I have my function. It says sketch a graph of this function. All right, so my initial value is 2.56. I know that this is an exponential growth function, so the value of my function is going to be increasing. So let's say 2.56 is down here, and that's what my function is going to look like, an exponential growth function. And while I'm at it, let me go ahead and label my axes. Again, I have t. This time t is in, let's see, t here is in days. And this is h, which is in centimeters. All right, so there's a sketch of my graph. What would the height of the plant be on the 5th day? Well, I have an equation here. I have a function that gives me the height of the plant for any value of t. This is just asking me what would be the value of the height on the 5th day. Well, I just take t equals 5 and plug it into my equation, and that tells me that on the 5th day my plant is going to be 250 centimeters tall. What is going to be the height of the plant on the 6th day? Well, I just enter that into my equation, 2.5 to to the power of 6, and that gives me 625 centimeters. Finally, part D says, find the doubling time for this plant. Now, let's take a look at what we know about the plant just based on the data in the table. It starts out at 2.56 centimeters, and then after one day it's reached 6.4 centimeters, and then after another day it's reached 16 centimeters. It looks to me like in just one day the height of the plant is more than doubling. Take a look at it going from day 2 to day 3. From day 2, it starts out at 16 centimeters on day 2, and twice 16 centimeters would be 32 centimeters. Well, it's already past 32 centimeters on day 3. So I'm going to expect that the doubling time of this plant is going to be something less than one day, since in one day it's growing more than twice the amount that it started with. So I'm expecting that the doubling time is going to be less than 1. So let's see if that turns out to be the case. So I want to know what's the doubling time. Let's say I start with this initial value here, 2.56. So 2.56, when the height of this plant doubles, so 2.56 times 2 is 5.12. So I want to know how long does it take the plant to grow from 2.56 centimeters to 5.12 centimeters. And again, I'm going to use this same approach that I used with half-life. I'm going to enter into my calculator y1 equals my equation 2.56 times 2.5 to the power of x, and I'm going to enter y2 equals 5.12, and I want to know what's the value of t at this intersection point right here. And my calculator tells me that when h, my height, equals 5.12 centimeters, then t equals 0.758 days. So therefore the doubling time for my plant is 0.758 days, and just as I expected, it takes less than one day for this plant to double in height.